Hello everyone and welcome back to Biology with Mrs. Evans. As you can see, I want to start talking about lab equipment activity. We've talked about designing controlled experiments. We've talked about analyzing data, constructing graphs. So let's take a moment and look at some lab equipment that you're going to use throughout the year. You have a sheet that has basically these items pictured on it, and you will be asked to fill out what they are used for and also to identify them as well. So let's go through that real quick. So A is the triple beam balance, and the triple beam balance, hopefully everybody knows and have had opportunities to use it, is used to measure mass. Beaker is B. What is a beaker used for? Yes, it can measure volume, but we typically don't use it to measure volume because it's not very accurate. So typically what we use a beaker for is to hold materials, to transport it from one location to the next. C, I don't care that you know the full name of this. This is a Erlenmeyer flask, and what we use an Erlenmeyer flask for is to mix basically materials. We would put material in there and then gently swirl it around in order to mix things safely. D, you will not use that, or as of yet we haven't used it. Who knows, maybe this year we'll come up with a way to use it. But that is a ring stand, and if you take chemistry you're going to use it a lot because each of those rings can hold different things. A beaker maybe in one, a thermometer in another, fun one another, etc. So that is a ring stand. E, that is a microscope. Hopefully you know what that is. Microscopes are used to see things that are basically too small to see with your naked eye. So we use it to see very small things up to a specific limit, basically. All right, so then we have, where are we at? F. F, yes, you guys probably know what the non-scientific name is for that. We're not calling them tweezers, we are calling them forceps. Forceps are used to basically transfer material safely from one container to, let's say, your beaker. You never want to use your fingers, etc. So we would use forceps. G, hopefully everybody knows what that is. That is a Bunsen burner. Bunsen burners obviously are used to heat materials up, etc. And let's see, H is a test tube rack. All right, we use that to hold test tubes for our lab experiments, to move our test tubes from one location to the next, etc. And obviously the test tubes inside of them are little tubes, and you need to know what that is as well. And then I is a funnel, and that is used to basically transfer materials from one container to another without making a mess, to do it safely. And then the last thing that you need to know is a graduated cylinder, and that is J, and graduated cylinder is used to measure volume precisely. All right, so make sure you know what each of these instruments are used for, because you will have a quiz on them, and I will, throughout the year, ask you to go grab these items, so you do need to know what they are. All right, so thinking like a scientist, we've already talked about observations in previous videos. So an observation, again, just remember, is gathering information using your senses. And basically I want to use this as a springboard. So observations tend to lead to inferences. Inferences are basically using your prior experience, your prior knowledge, to come up with the best explanation for what you're observing. So let me switch to the next slide. So here are two hostas, and these are two plants that actually my husband and I planted, let's see, 6 years ago now. And you notice that the one on the right is significantly bigger than the one on the left. And let me get to the pointer. So you can see this hosta here is significantly bigger than this hosta here. So what observations can you make? Obviously, we just said that one is bigger than the other. It looks like that maybe this one gets a little bit more sunlight than this one does. You notice that there are some trees in the back. Looks like I need to weed that area. But those are all observations. So based on those observations, what kind of inferences can you make? So why do you think this one is bigger than this one? So you might say, well, this one maybe is older than the one on the left. This one is getting more sunlight, so it's growing bigger than the one on the left. Um, all of those are inferences that you can make based on your previous experience. So I will tell you actually that these two hostas were planted at the same time. They were the same size that, when we planted them. And realistically, if you look at the amount of sunlight that each of these get, they get about the same amount of sunlight each day because of the way the basically the shade shifts and stuff like that. So having basically eliminated those two reasons as to why one is bigger than the other, you might be wondering, well, what's going on there? And that's an actual question that my husband asked me, being the scientist. He said, well, why is one bigger than the other? And the reason why is because the tree in the back here, when we planted it, this one had a massive root, basically, and we basically still planted it there because it said it only needed a certain depth. And then this one, there was no obstructions, and so as you can see, the tree appears to be also impacting the amount of nutrients maybe that this one is getting. So observations lead to inferences. Inferences lead to hypotheses. We've already talked about a hypothesis. A hypothesis is an educated guess. Sorry, it is a proposed explanation for observations. All right, so let me go ahead and click to the next slide. All right, science is a way of knowing. Humans are skeptical. All right, we always ask the question as to why. How do you know? Science is changing. It is not. What is true one day may not be true the next because of basically advances in technology. It's a wheel, if you will. We increase technology, that increases knowledge into science, and then that increase in knowledge in science leads to advances in technology. So there's just this cycle. So we're constantly getting better. So scientists, we basically come up with the idea of what we think is true. Doesn't mean it necessarily is true, because new technology, new discoveries may lead us to change those ideas. Probably the biggest one is that for that is back in Christopher Columbus's day. Everybody thought the world was flat, and he went out and explored the world. And now with telescopes and satellite images and exploration in space, we know that no, the world's not flat, it's round. Another example of changing in technology, how it's led to changes in scientific knowledge, is that scientists used to think that there was no life beyond a certain point in the ocean because basically sunlight stops hitting at a certain depth. So if photosynthesis couldn't occur because there's no sunlight, then scientists believed that there was no life down at the very deep parts of the ocean. But once we were able to create a submersible to go down and explore those depths, then scientists discovered, wait a minute, that these areas are actually teeming with life. So that led to the question as to, okay, why are they so successful living down here? What's their energy source? And then scientists basically designed experiments to test it. They found that, hey, the hydrothermal vents that are down there, they're spewing sulfides, and they're using that basically the sulfur and stuff that's coming off of that to create their own food. So instead of doing photosynthesis, they're doing what is called chemosynthesis, using chemicals to make food. So changes in technology changes our views in science. So that some things are changing. Again, think about Pluto. When I was in school, we learned our planets, and good old Pluto was a planet, and now he has been downgraded, or she has been downgraded to a dwarf planet, and who knows, maybe within the next year or two, she may be, or he may be, or it may be upgraded back to a planet status. All right, so we've been talking about the scientific method, so let's take a moment and look at some experiments that happened in the 16, 17, and 1800s. So spontaneous generation is a belief that people had for a long period of time. They believed that living things could spontaneously generate from non-living material. So let's say you leave a pack of crackers out on the counter, you go away, you come back, and and you notice that there is a mouse there. People would believe that the mouse just basically spontaneously appeared. And obviously today we know that is not the case, that there is a parent organism for that mouse, and maybe that we know that the mouse just happened to come upon our crackers and decide to eat it. But back then they believed in spontaneous generation. So Francisco Redi is a scientist that basically started to question the idea of spontaneous generation, so he decided to design an experiment. So let me go ahead and advance the slide so you can see what he looked like. So he designed an experiment to test his hypothesis, basically that maggots come from flies. They don't just appear from meat itself. So he designed an experiment, and there's some discrepancies about how he designed his experiment. Some resources say that he used 2 jars. Some resources say that he used 3 jars. There's some discrepancy about the coverings on the jar. You'll see in one source it'll say that he used paper to completely seal the jar off, and another source it'll say that he used cork. So for us, we're going to say that he used 3 jars, and that one jar was open to air, another jar was sealed with, we're going to say, cork, and then another one he covered with cheesecloth. And cheesecloth basically allows air to enter the jar but keeps the flies off. So again, I'm going to advance the slide so you can see the experiment. So what he noticed is that the one that was open to air, obviously a couple of days later, he noticed that flies came, and then a few days later that maggots appeared. The one that had cheesecloth on it, the flies came, visited the container, and a few days later maggots did appear, but they appeared on top of the cheesecloth. And then the one that was completely sealed off, and again I'll advance the slide, the one that was completely sealed off, we're going to say again that it was with cork, maggots did not appear. So basically he said, hey, I just disproved the idea of spontaneous generation. Obviously flies are laying eggs, and then that's how the maggots are appearing. Again, people disbelieved or did not accept his basically his experiment. They said all you basically proved was that oxygen was a necessary element for spontaneous generation to occur. So then another scientist by the name of John Needham, he designed an experiment because he believed that spontaneous did happen, but it happened for microscopic organisms. So he took a flask, he heated it, and then he had basically a broth that he had in it. And after a few days, the one that was open to air became cloudy. So he said, hey, look, obviously spontaneous generation does occur for things that are microscopic. So Spallanzani said, no, I don't think that is true. So he designed an experiment in the 1700s to basically fix Needham's experiments, because Spallanzani said basically you didn't heat the material long enough to kill any bacteria that was in the broth that you used, nor did you heat the flask that you put the broth in, so there may have been some microscopic organisms living on the flask. So Spallanzani said, hey, I'm going to heat the flask and the broth for a certain period of time to kill off anything. And he sealed one of the flasks and he left one open. So over time, what happened was the one that was sealed did not show any growth in it, but the one that was open to air did show basically that bacteria was growing. So he said, hey, look, there is a parent organism, and it's basically bacteria that's in the air that is causing the cloudiness in this broth. So again, people didn't believe or basically said, you just showed that, again, oxygen is necessary for spontaneous generation to occur. So Louis Pasteur in the 1800s, 1859, 1863, designed an experiment to basically put it to rest. He used a flask, and he designed the flask to look like what you see here. And we refer to this as a gooseneck. I think some books will refer to it as a swan neck. What he did was he basically heated the flask so that this area here, when he heated it, he could then stretch it into this structure here that you see. So what he did is he followed pretty much Spallanzani's approach. He heated the broth and he heated the flask themselves to sterilize it, and he then heated the neck of the flask that you see here and made it into this structure. And he put the broth in. He left one in the flask so that it looked like this the entire time, and then in the other flask he broke the flask off right here so that air could freely move into the flask. And then the design of this particular gooseneck flask was basically, he designed it so that he basically thought that bacteria and things like that would get trapped here. So what he did is he conducted his experiment, and lo and behold, the one that was in here had become cloudy, and then this one basically remained clear. So he basically put it to rest that spontaneous generation doesn't occur, because he did allow, from the design of the flask, that air could still come in to the flask, but it would trap any material into this area, and basically he disproved the idea of spontaneous generation. And to further show that to, again, the disbelievers, he tilted the flask so that the broth could collect in this area, and then after a few days, then this area right here became cloudy. So he finally put the idea of a spontaneous generation basically to bed. Okay, so hypotheses, they can lead to the development of a theory. So a theory is a well-tested hypothesis that has basically been tested many times, and each time results in basically the same information being obtained. So it's usually the work of several different scientists conducting similar experiments and coming up with the same result. So the work of Redi, Spallanzani, and Pasteur led to the idea of basically life coming from life. So that led to the theory of biogenesis, as you saw earlier in the slide. So the theory of biogenesis is that life must come from life. So the difference between a theory and a law is basically, a law describes basically an action that we see in nature. It usually has a mathematical component to it. The law of gravity, obviously what goes up must come down, but probably the most famous thing that you are probably familiar with as far as laws go is Newton's laws of motion. You know, an object at rest stays at rest unless acted upon by an outside force. An object in motion stays in motion, again, unless acted upon by an outside force, etc. So laws describe basically an action, and theories basically explain how nature works.